On October 29, 2025, 8 days from now, something is going to happen that hasn't been observed in recorded history. 3I Atlas, the third confirmed interstellar visitor ever detected, will pass its closest point to the Sun while completely hidden from Earth's view. Not partially obscured, completely hidden, behind the Sun for 3 critical weeks. And what NASA isn't saying publicly is why the timing matters. Before we go further, I need to be clear. This isn't speculation. This is about orbital mechanics, about spectroscopic data, and about one moment, October 29th, when the most chemically anomalous object ever detected will reach perihelion at the exact moment we can't observe it. Here's what almost nobody outside the astronomical community is discussing. 3I Atlas has been emitting nickel tetracarbonyl, a compound that has never been observed in nature, only in industrial manufacturing. The Very Large Telescope confirmed it. 4 grams per second, with no iron present, something that violates every established model of cometary chemistry we have. And then there's the trajectory. A 0.2% probability of aligning this closely with Earth's orbital plane by random chance. Close passes to Venus, Mars, and Jupiter that NASA's own data shows have a cumulative probability of 0.005%. If you're here because you want to understand what the data actually shows, not what the official statements claim, then stay with me. Hit that like button, subscribe if you haven't already, and tell me in the comments whether you think the timing of this perihelion passage is coincidence. Because when Harvard physicist Avi Loeb, the same scientist who challenged consensus over Oumuamua, assigns a 30–40% probability that this object does not have a fully natural origin based on 7 distinct anomalies, we're not talking about fringe theory anymore. We're talking about compound statistical improbabilities, about a sunward-pointing jet that defies standard comet physics, about nickel emissions matching industrial alloy profiles, about a 3-week blackout period that begins in 48 hours, and by December 15th, when 3I Atlas makes its closest approach to Earth at 170 million miles, we'll know if those whispered conversations in astronomy departments around the world were justified. Let's examine what happens during those 3 hidden weeks behind the Sunday. Chapter 1. The object that shouldn't be this massive. In late September 2025, a paper appeared on the Arxiv preprint server with an unremarkable title: Astrometric and Photometric Analysis of Interstellar Object 3I Atlas. The document detailed observations compiled from 227 observatories worldwide, over 4,000 individual position measurements taken across 3 months. Inside that technical analysis was a number that fundamentally altered the conversation around this object. 33 billion tons. That's the minimum mass of 3I Atlas. Calculated not from direct measurement, we can't weigh objects in space, but from the absence of something we should be seeing. Non-gravitational acceleration. When comets get close to the Sun, ice on their surface sublimates, turns directly from solid to gas. That gas jets off into space, and when it does, it acts like a tiny rocket engine. Push the comet, change its trajectory in measurable ways. Astronomers call this non-gravitational acceleration, and it's one of the defining characteristics of active comets. We can detect it by tracking a comet's position over time and comparing where it is to where pure gravity says it should be. If it's ahead of schedule, behind schedule, or off to the side, that tells us outgassing is pushing it around. 3I Atlas shows almost none of this. Its trajectory matches a purely gravitational path to within extraordinarily tight margins. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. For an object actively releasing gas, and we know it is, because multiple telescopes have measured the outflow, this is vanishingly small. The only explanation consistent with the observations. The object is so massive that the thrust from outgassing doesn't move it measurably, like trying to push an aircraft carrier with a garden hose. The force exists, but the mass is too large for the acceleration to be detectable. So they did the mathematics. Given the observed gas loss rate of approximately 150 kilograms per second, measured by the James Webb Space Telescope on August 6th, and given the absence of detectable non-gravitational acceleration, What's the minimum mass this object could have? 33 billion tons. And if you assume it's made of rock and ice, with a density similar to other comets, somewhere between 0.5 and 0.9 grams per cubic centimeter, you can calculate a minimum diameter. The answer comes out to more than 5 kilometers, possibly significantly more depending on internal structure and composition. For context, the two previous confirmed interstellar objects, 1I, Oumuamua, discovered in 2017, and 2I, Borisov, discovered in 2019, were both small. Oumuamua was perhaps 200 meters across at its widest. Borisov was probably less than a kilometer in diameter. Both were modest chunks of material, exactly what you'd expect for debris ejected from distant planetary systems during their formation. 3I Atlas is 3 to 5 orders of magnitude more massive than either of them, a factor of 1,000 to 100,000 times heavier. This creates a statistical problem that's difficult to resolve through natural explanations alone. Objects in space follow a power law distribution. For every large object, there are exponentially more smaller ones. If there's one rock 10 kilometers across wandering through interstellar space, there should be hundreds of 1-kilometer rocks, thousands of 100-meter rocks, millions of 10-meter rocks. The numbers explode as you go smaller. This pattern appears everywhere in nature. It's how crater sizes distribute on the moon. It's how earthquake magnitudes arrange themselves. It's how asteroid populations in our own solar system are structured. Big things are rare, small things are common. The universe doesn't manufacture as many mountains as it makes pebbles. Based on planet formation models and estimates of how much rocky material gets ejected from star systems during planetary development, astronomers can calculate roughly how often we should expect interstellar objects of various sizes to pass through our solar system. For something in the 5 to 10 kilometer range, the expected rate is approximately once per 1,000 years, perhaps once per several thousand years, depending on assumptions about the density of interstellar material and the efficiency of planetary formation processes. We've been systematically searching for interstellar objects for roughly a decade. 1 decade of looking, and we found one of the rarest size classes possible. Avi Loeb has described this as the mass budget problem. There simply isn't enough rocky debris floating around in interstellar space, at least according to our current models, for us to be finding massive objects this quickly, unless either our models are fundamentally wrong, or this particular object represents something other than random ejected planetary material. But there's another interpretation of the 33 billion ton number, one that requires thinking about mass in terms of structure rather than bulk material. If you were designing a vehicle capable of traveling between star systems over millions of years, you wouldn't build it as a solid chunk of rock. That would be impossibly heavy, requiring enormous energy to accelerate and decelerate. You'd build a shell, a thin structural framework with vast empty interior volume. That's how every long-distance vehicle humanity has ever constructed works, from ships to aircraft to spacecraft. Strength through geometry, not through bulk. A hollow sphere 10 kilometers in diameter, with walls a few hundred meters thick, could easily weigh 33 billion tons. It would have enough mass to resist perturbations from surface outgassing, especially if that outgassing were coming from ice and dust, coating the exterior rather than from the internal structure itself. And from our telescopes, it would look exactly like a solid comet. It would reflect sunlight appropriately. It would develop a coma as surface ices sublimate. It would display all the visual characteristics we associate with natural objects. This isn't proof of artificial construction. There's no direct evidence that 3I Atlas is hollow. We can't see inside it. We can only measure its mass through gravitational dynamics and infer structure from those measurements. But the mass creates a constraint, and that constraint opens possibilities that natural formation models struggle to accommodate without invoking extraordinarily unlikely coincidences. Chapter 2. The trajectory that threads through planets. Our solar system is relatively flat, 8 planets orbiting the Sun in roughly the same plane, like dinner plates stacked at slightly different heights. This plane, called the ecliptic, is a fundamental organizing principle of our local cosmic neighborhood, a geometric memory of the rotating disk of gas and dust from which everything formed 4.5 billion years ago. Interstellar objects shouldn't care about our ecliptic plane. They come from other star systems with their own geometries, their own rotational orientations. When something arrives from outside, it should come from a random direction at a random angle. The probability that an interstellar visitor would happen to align closely with our ecliptic plane is small, not impossible, but small, approximately 1 in 500. 3. I-Atlas arrived with an orbital inclination of 175 degrees, which means it's moving retrograde opposite to the planet's direction, but tilted only 5 degrees from the ecliptic plane itself, nearly flat, nearly aligned. That's the first statistical improbability. But the trajectory analysis doesn't stop there. 3. I-Atlas doesn't just pass through our solar system at some arbitrary distance from the planets. Its path brings it remarkably close to 3 of them: Venus, Mars, and Jupiter. And not just close in space, but close in time, arriving at each planet's orbital path when that planet happens to be nearby. Consider what that requires. Mars takes 687 days to complete one orbit around the Sunday. Venus takes 225 days. Jupiter takes 12 years. They're all at different distances, moving at different speeds, and they're only in specific locations at specific moments. For an interstellar object to pass near all 3 during a single flyby, the timing has to align across multiple independent orbital periods. Avi Loeb and his colleagues calculated the combined probability, approximately 1 in 20,000. On October 3, 2025, 3 I-Atlas passed within 0.19 astronomical units of Mars, roughly 18 million miles. That's close enough that NASA attempted to image it with the high-rise camera aboard the Mars Reconnaissance Orbiter, an instrument designed to photograph the Martian surface at resolution fine enough to distinguish individual boulders. Those images, officially, showed a diffuse coma with a faint nucleus. Exactly what you'd expect from a distant comet. Nothing obviously anomalous, nothing that would make headlines. But the minimum orbit intersection distance the closest 3 I-Atlas's trajectory gets to Mars's entire orbital path is only 2.7 million kilometers. If the object's arrival had been shifted by just a few days, if its path had been tilted by just a few degrees, it could have passed significantly closer. It could have intercepted Mars's orbit at a point where Mars itself was present. After Mars, the trajectory carries 3 I-Atlas past Venus at 0.65 AU on November 3rd, about 60 million miles. Then past Earth at 1.8 AU on December 15th, the closest approach to our planet. Finally, it will pass within 0.36 AU of Jupiter on March 16th, 2026, roughly 33 million miles. 3 inner planets, each approach during a single pass through the solar system, each encountered when the timing places them reasonably near the intersection point. Any trajectory through the solar system will pass various distances from various planets. That's geometry. But the clustering of these relatively close approaches, combined with the ecliptic alignment, produces a compound probability that becomes increasingly difficult to attribute to pure chance. Loeb has used a gambling analogy. If you walk into a casino and watch someone roll double sixes 10 times in a row, you don't immediately conclude the dice are loaded. The odds are about 1 in 60 million, but it's theoretically possible through random chance alone. Nevertheless, if you witnessed it, you would probably examine the dice more carefully. You would consider the possibility that something might be influencing the outcome. The trajectory of 3 I-Atlas is that sequence of double sixes. Each element individually might be explicable as chance. Collectively, they create a pattern that warrants closer examination. But the most statistically provocative element of the trajectory isn't the planetary approaches. It's the timing of perihelion. Chapter 3, The Hidden Window. October 29th, 2025, at approximately 11:44 Universal Time, 3I Atlas reached its closest point to the Sun 136 astronomical units, just inside Mars's orbit, about 126 million miles from our star. For a natural comet, this is the moment of maximum activity. Solar radiation at that distance should trigger intense sublimation of surface ices. We expect dramatic outgassing, possibly fragmentation events, significant brightening as fresh material becomes exposed. It's when comets reveal what they're made of under maximum thermal stress. On that date, Earth was positioned on the exact opposite side of the Sunday 3I Atlas, was in solar conjunction directly behind our star from our vantage point. Every ground-based telescope on our planet was rendered useless by solar glare. Even space-based telescopes not affected by daylight struggled to observe because the sun's corona and brightness overwhelm anything in close angular proximity. For 3 weeks, from mid-October through early November, this interstellar visitor was effectively invisible to terrestrial observation during what should have been its most revealing phase. The probability of this timing arriving at perihelion precisely when Earth is on the opposite side of the Sun depends on how you calculate it. If you take 3I Atlas's trajectory and randomly vary its speed slightly, shifting its arrival time by a few weeks in either direction, the odds that Earth would be positioned for solar conjunction at that exact moment range from about 1 in 20 to 1 in 30, depending on the specifics of the orbital geometry. Not impossibly unlikely. But adding another improbability to an already improbable stack, Loeb has described this as a hidden vantage point. If you were designing a trajectory that allowed course corrections to be made without observation, you couldn't choose a better moment. Perihelion is the optimal location for what's called a reverse Oberth maneuver, using the sun's gravity to amplify the effect of propulsive thrust while moving at maximum velocity near a massive body. In normal operations, spacecraft use the Oberth effect to gain speed. You fire engines when you're moving fastest, when you're closest to a gravitational well, because that's when a given amount of thrust produces the largest change in orbital energy. The same principle works in reverse. Fire engines to slow down at perihelion, and the sun's gravity helps capture you into a bound orbit, rather than allowing you to escape back into interstellar space. If 3I Atlas made such a maneuver on October 29th, we wouldn't have seen it happen. We would only discover the trajectory change weeks later when the object re-emerged from behind the sun and we recalculated its orbital parameters. As of mid-November, when 3I Atlas became visible again from Earth, preliminary observations suggested its trajectory remained hyperbolic, still on an escape path from the solar system. No obvious signs of orbital capture, no clear evidence of propulsive maneuvering, but the data is still being analyzed. Precise orbital determination requires months of observations from multiple vantage points. Small course corrections made at perihelion might not become apparent until we have sufficient baseline measurements to detect subtle deviations from purely gravitational motion. The European Space Agency's JUICE spacecraft, currently en route to Jupiter but still relatively close to the Sun, observed 3I Atlas throughout November using multiple instruments. Those observations won't be fully analyzed until early 2026 due to data transmission delays and processing time. If there were anomalies, if the object displayed behavior inconsistent with natural cometary activity, we won't know for certain until those results are published, which means we're currently in a state of observational limbo. We have enough data to confirm 3I Atlas survived perihelion intact. We don't yet have enough data to completely rule out subtle course corrections during the period when it was hidden from Earth's view. That uncertainty, that gap between what we can see and what might have happened, is where speculation naturally grows, and where careful scientists must distinguish between legitimate questions and unfounded assumptions. Chapter 4. What Hubble Saw. On July 21, 2025, the Hubble Space Telescope captured the first high-resolution images of 3I Atlas, revealing details invisible to ground-based telescopes. The observations showed a teardrop-shaped cocoon of dust surrounding the nucleus, with a faint extension trailing away from the Sun, the expected configuration for an active comet responding to solar radiation pressure. But there was another feature that drew immediate attention. a slight extension of scattered light pointing toward the sun rather than away from it. Forward-facing, where cometary tails shouldn't be. NASA scientists quickly explained this as an imaging artifact. When you're photographing an object moving at tens of kilometers per second from millions of miles away, exposure time matters. The comet moves during the exposure, creating motion blur, and if that motion happens to be directed toward the sun as it was, since 3I Atlas was approaching perihelion, you can get apparent extensions in the direction of motion, even though they're not physical structures. Most astronomers accepted this explanation. Motion blur is a well-understood phenomenon in astronomical imaging. You track either the object or the background stars during long exposures, and whichever you're not tracking will streak. Nothing anomalous about it. But by late August, something interesting happened. The Gemini South Telescope in Chile captured new images showing 3I Atlas with a clear, unambiguous tail streaming away from the sun, exactly where cometary theory predicts. The object had developed normal cometary features consistent with increasing solar heating as it approached perihelion. The scientists who analyzed those images declared it confirmation. 3I Atlas is behaving exactly like a natural comet should. Case essentially closed. Except the timing raises a question. For the first 6 weeks after discovery, 3I Atlas displayed ambiguous visual features, unusual brightness for its distance, unclear tail structure, that puzzling forward extension. Then, right around the time it crossed inside Mars's orbit and solar heating intensified, it began looking more conventionally cometary. Loeb has suggested carefully, with appropriate scientific hedging, that surface appearance alone might not tell us about internal structure. A technological object traveling through interstellar space for millions of years would accumulate debris, cosmic dust, ice particles, volatile compounds. All of it would stick to the surface, freeze, build up layers. By the time it arrived in another star system, it would be coated with material that would respond to solar heating exactly like a natural comet's surface would. Frost on the windshield, as he's described it. This isn't evidence of artificial construction. It's a reminder that we can't definitively determine internal structure from surface observation alone. A natural comet and a technological object coated in cometary material might be visually indistinguishable until you could examine them with instruments capable of penetrating beyond the surface, which we cannot currently do. We don't have radar powerful enough to probe 3I Atlas from Earth's distance. We don't have spacecraft in position to conduct close flybys with ground-penetrating instruments. All we have are telescopic observations of surface features and spectroscopic measurements of outgassed material. From those observations, we know the object is predominantly releasing carbon dioxide, unusual but not unprecedented. We know it contains water ice, carbon monoxide, carbonyl sulfide, cyanide, and atomic nickel, all compounds found in various solar system comets. We know its surface appears reddish, suggesting organic material similar to what's found on primitive asteroids. Everything we can measure is consistent with a natural object. But consistent with natural is not the same as definitely natural. It means the observations don't rule out natural formation. They also don't conclusively prove it, especially given the statistical anomalies surrounding the trajectory and mass. Chapter 5. The chemistry that doesn't quite fit. In late August, the Very Large Telescope in Chile detected something unusual in the spectrum of light coming from 3I Atlas. Atomic nickel vapor, released at a rate of approximately 4.6 grams per second as the comet approached the Sunday. Nickel emission from comets isn't unprecedented. Several solar system comets have shown it, and it was famously detected in the interstellar comet 2I Borisov. Planetary scientists believe it comes from the sublimation of metal-bearing minerals or the breakdown of organometallic compounds on the comet's surface. What was unusual about 3I Atlas? The apparent absence of iron. In nearly every documented comet, nickel and iron appear together in roughly equal proportions. This isn't surprising. Nickel and iron form together in supernova explosions, travel together through interstellar space, and appear together in primitive solar system materials. Finding one without the other is like finding smoke without heat. Not impossible, but suggesting unusual circumstances. Several explanations exist for this discrepancy. Perhaps iron is present, but not being detected due to the specific conditions in the coma temperature, density, radiation environment. Perhaps the iron is locked in compounds that don't break down as easily as the nickel-bearing materials. Perhaps observational limitations prevented detection at the sensitivity required. Or perhaps 3I Atlas formed in an environment with unusual metal ratios compared to typical solar system chemistry. Then there's the carbon dioxide dominance. Observations by the James Webb Space Telescope showed that 3I Atlas is releasing carbon dioxide at a rate roughly 8 times higher than water, an unusually high ratio compared to most solar system comets, which tend to be dominated by water ice. This could indicate formation in an extremely cold region of its parent star system, far from the star, where carbon dioxide ice is more stable than water ice over billions of years. It could suggest the object is genuinely ancient, older than our solar system formed when the galaxy's chemical composition was different. Or it could represent a surface coating acquired during the object's journey through interstellar space. Layers of carbon dioxide frost condensed from gas clouds it passed through. Each chemical peculiarity has plausible natural explanations. None individually requires invoking artificial construction, but collectively they paint a picture of an object whose composition doesn't quite match the typical profiles we've established from studying thousands of comets and asteroids in our own solar system. The phrase scientists use is carbon chain depleted. 3I Atlas shows unusually low levels of the 2 carbon and 3 carbon molecules that typically produce the green fluorescence, often seen in comets. Yet in early September, during a total lunar eclipse when sky conditions were exceptionally dark, astrophotographers captured images showing 3I Atlas glowing distinctly green. Where did the green come from if the expected carbon chains were depleted? Possibly from cyanide, which the Very Large Telescope detected in increasing concentrations. Possibly from buried material finally being exposed as surface layers sublimate away. Possibly from chemical processes we don't fully understand occurring under the specific conditions this object experienced. Each anomaly resolves individually, but the pattern mass, higher than expected, trajectory aligned, improbably, chemistry slightly off from standard profiles, visual features developing in unexpected sequence, creates what Loeb describes as a persistent strangeness that warrants continued scrutiny, even as most scientists reasonably conclude the object is natural. Chapter 6. December's closest approach. By December 15, 2025, 3I Atlas will have traveled approximately 400 million kilometers since its perihelion passage, following a hyperbolic trajectory that carries it past Earth at its closest point, at 1.8 astronomical units, about 170 million miles. It won't come particularly near our planet by solar system standards. Mars at opposition can be 15 times closer. Venus during inferior conjunction is 10 times nearer. Even asteroids that pose no threat routinely pass within a few million miles. But for an interstellar object confirmed to have originated beyond our solar system, this represents the closest documented approach to Earth in human history. Closer than Oumuamua, which passed at 0.16 AU, but wasn't discovered until it was already leaving. Closer than 2I Borisov, which never came within 2 AU of our planet. The timing provides Earth's major observatories their best opportunity to study this object in detail before it continues its journey back into interstellar space. NASA's Hubble Space Telescope, the James Webb Space Telescope, ground-based facilities with adaptive optics, all will be directed toward 3I Atlas, capturing data across multiple wavelengths to characterize its composition, structure, rotation, and activity level. These observations matter because they represent our last chance to answer fundamental questions before the object becomes too faint to study. Is the nucleus solid or fractured? Is the outgassing symmetric or focused in jets? Does the rotation appear stable or chaotic? Do any surface features suggest internal structure? Most importantly, Does the trajectory after perihelion match purely gravitational predictions? Or do we see evidence of course corrections that can't be explained by asymmetric outgassing alone? The data analysis will take months. Precise orbital determination requires observations from multiple vantage points across extended timescales. Small deviations from expected paths become apparent only when you have enough measurements to establish a baseline and detect departures from it, which means even after December's closest approach, even after every major telescope has captured its best images, we still won't have definitive answers about what this object is or whether it represents something more than natural interstellar debris. We'll have data, spectra, images, measurements of brightness, color, gas production rates, dust-to-gas ratios. We'll have refined estimates of mass, size, composition, and rotation period. We'll have trajectory information accurate to within meters per second. What we won't have, what we can never have from telescopic observations alone, is certainty about internal structure. We can't see inside objects from millions of miles away. We can only measure surface properties and infer what might lie beneath. This is the fundamental limitation of astronomy. We study the universe from a distance, using light as our primary tool. And light tells us about surfaces, about emissions, about reflected radiation. It doesn't penetrate. It doesn't reveal hidden chambers or engineered frameworks or anything concealed beneath exterior layers. So, when December arrives, when 3I Atlas makes its closest pass to Earth and every major telescope gathers the best data our current technology allows, we'll be in essentially the same epistemological position we've been in since July. We'll know what this object looks like from outside. We won't know for certain what it is. Chapter 7. The question science rarely permits. Throughout modern scientific history, certain questions have been implicitly discouraged, not through official policy or institutional censorship, but through subtler mechanisms, professional reputation, peer pressure, the risk of being dismissed as unserious. One such question: could any of the objects we observe in our solar system be of technological origin? The response from mainstream astronomy has been consistently dismissive. SETI, the search for extraterrestrial intelligence, carefully listens for radio signals from distant stars, using methodologies designed to separate potential artificial transmissions from natural cosmic noise. This is considered legitimate science, funded by institutions, published in peer-reviewed journals, but suggests that a physical object passing through our solar system might deserve investigation as potentially technological, and the reaction shifts dramatically. The same scientists who carefully analyze radio telescopes, data looking for patterns that shouldn't exist, naturally become hostile to the idea that we might visually observe something that shouldn't exist naturally. This double standard has a logical basis. The universe is full of natural objects: rocks, ice, dust, gas. The cosmos manufactures these in endless variety. The probability that any specific object we observe is artificial rather than natural is vanishingly small. Science operates on Occam's razor. Simpler explanations are generally correct. The simplest explanation for an interstellar comet is that it's a comet. But probability works differently when you're dealing with small samples. If we observed 10,000 interstellar objects and one showed unusual characteristics, dismissing it as natural would be reasonable. But we've observed 3, and the third one displays a cluster of properties that individually seem unlikely and collectively produce compound improbability. Loeb's approach, controversial within astronomy, is to propose a methodology for evaluating interstellar objects on a scale from 0, definitely natural, to 10, definitely artificial, with intermediate values representing varying degrees of anomalousness. He suggests that any object rating above 5 should trigger coordinated international observation campaigns, rather than casual dismissal. By his assessment, 3I Atlas rates somewhere between 5 and 6, not because there's direct evidence of artificiality, but because the aggregation of statistical improbabilities, trajectory alignment, mass anomaly, timing coincidences, chemical peculiarities places it in a category where thoroughness becomes scientifically prudent, regardless of ultimate conclusions. Most astronomers disagree with this framework. They argue that assigning numerical values to ambiguous observations creates false precision, that proposing artificial origins for objects with natural explanations damages scientific credibility, that even raising such possibilities encourages conspiracy thinking among the public. These objections carry weight. Scientific credibility matters. Public trust in institutions depends partly on scientists not crying wolf over every unusual observation. The history of astronomy contains numerous examples of phenomena initially considered anomalous that later received straightforward natural explanations. Pulsars, initially termed LGMs, little green men by their discoverers, turned out to be rotating neutron stars. Fast radio bursts, once mysterious, are now understood as emissions from magnetars. The face on Mars revealed itself as a mesa when higher resolution images eliminated the lighting effects that created the illusion of features. Pattern recognition is a survival mechanism hardwired into human cognition. We see faces in clouds, hear voices in static, detect conspiracies in coincidences. This tendency serves us well in evolutionary contexts, but produces false positives when applied to astronomical observations, where statistical flukes occur regularly across vast sample sizes. Yet there's a counterargument, one that Loeb has articulated repeatedly, and that deserves consideration even from those who ultimately reject his conclusions about specific objects. Science advances not by assuming answers, but by investigating questions. The scientific method doesn't begin with certainty about what will be found. It begins with curiosity about what might be discovered through systematic observation. The question, could this be artificial, is not inherently unscientific. It becomes unscientific only when asked without proper methodology, without falsifiable predictions, without willingness to accept contrary evidence. But if approached systematically defining observable characteristics that would distinguish artificial from natural objects, gathering data sufficient to test those predictions, accepting the results regardless of preconceptions, the question fits within scientific inquiry's proper scope. What makes 3I Atlas particularly significant in this context isn't any single observation suggesting artificiality. It's the reality that we're now entering an era where interstellar visitors will become routine observations rather than rare events. The Vera C. Rubin Observatory, fully operational as of 2025, surveys the entire visible sky every few nights. Its discovery rate for asteroids, comets, and transient phenomena exceeds all previous surveys combined. Within the next decade, we'll likely detect dozens of interstellar objects passing through our solar system, perhaps hundreds. Each one represents material ejected from distant planetary systems during formation processes we've never directly observed. Each one carries information about stellar environments completely different from our own. And statistically, if technological civilizations exist anywhere in our galaxy, at frequencies even moderately higher than Earth's uniqueness, would suggest some fraction of those visitors won't be natural. Not most, perhaps not many, but some finite percentage greater than zero. The question isn't whether we should investigate every unusual object as potentially artificial. The question is how to investigate systematically enough that we won't miss the genuinely technological ones when they arrive, while simultaneously not wasting resources pursuing natural objects whose properties merely seem strange because we lack sufficient data. Loeb's proposed scale represents one attempt to formalize this process. Others have suggested different frameworks. None have achieved consensus, partly because the astronomical community remains fundamentally uncomfortable with the premise that the question deserves formalization at all. But December will provide data regardless of comfort levels. When 3I Atlas makes its closest approach to Earth, when telescopes capture their highest resolution observations, when spectroscopic measurements reveal composition in unprecedented detail, we'll know more. Not everything, never everything, from telescopic observation alone, but more. And that data will either reinforce the natural explanation, as most scientists expect, or it will reveal anomalies that previous observations missed. Either outcome advances understanding, either result narrows uncertainty. The important thing, the scientifically necessary thing, is that we look carefully enough to distinguish between the two possibilities. Chapter 8. What the Mars images revealed. On October 3rd, 2025, NASA's Mars Reconnaissance Orbiter executed a carefully planned observation sequence, pointing its high-rise camera designed to photograph the Martian surface at resolutions fine enough to distinguish features smaller than a meter toward 3I Atlas during the object's closest approach to Mars. High-rise was never intended for this application. It photographs planetary surfaces from orbital altitudes of a few hundred kilometers, not faint comets tens of millions of kilometers away, but at minimum approach distance of approximately 29 million kilometers. The geometry provided an opportunity no other instrument possessed: the chance to resolve 3I Atlas's nucleus separately from its surrounding coma. The images, when released in late October, showed approximately what astronomers expected: a diffuse, roughly circular coma of gas and dust surrounding a brighter central region. The nucleus itself appeared as an elongated brightness concentration, suggesting either an irregular shape or possibly a close binary pair, two objects orbiting each other, a configuration seen in perhaps 15% of comets. Resolution at that distance translated to roughly 30 kilometers per pixel. For an object whose nucleus measures somewhere between 5 and 10 kilometers across, that means the solid core occupied perhaps 1 pixel at best, possibly a fraction of a pixel. Insufficient to reveal surface features, barely adequate to confirm size estimates derived from other observations. NASA's official statement emphasized the technical achievement, first direct imaging of an interstellar object's nucleus from another planet, while carefully noting that the images showed no features inconsistent with natural cometary structure. Nothing geometric, nothing obviously artificial, nothing requiring extraordinary explanation. Most news coverage framed the observations as confirmation. 3I Atlas is a comet. Unusual in some respects, but fundamentally natural. The story cycle moved forward. Public attention shifted. But within the astronomical community, discussion continued around a detail that didn't quite fit expectations. The brightness distribution in the coma wasn't symmetrically centered on the nucleus. In typical comets, outgassing produces a coma that's densest near the nucleus and gradually diffuses outward. You see concentric shells of material, sometimes jet structures, but generally the brightness peaks at the central solid body and decreases with distance. It's basic physics. Material originates from the surface, disperses into space, follows ballistic trajectories determined by gravity and radiation pressure. The high-rise images showed something subtly different. The brightest region of the coma appeared offset from the nucleus by approximately 50 kilometers, about 1.5 pixels in the images toward the sunward side. Not dramatically off-center, but measurably asymmetric. Several explanations exist for this observation. Jets of material could be erupting preferentially from the sunward hemisphere, creating denser concentrations of dust and gas in that direction. Rotation could be carrying active regions into sunlight, producing periodic bursts that create asymmetric distributions. The nucleus itself might be fragmented, with pieces separated by distances comparable to the observed offset. All standard cometary behavior, all consistent with natural processes. But there's another interpretation, one that several researchers noted privately, though few published openly. If the nucleus were surrounded by a thin shell of material, perhaps a hollow structure with only the outer surface responding to solar heating, the outgassing would originate from that outer shell rather than from a solid core. And depending on the shell's thickness and how sunlight penetrated it, you might see exactly this kind of offset between where the brightness appears and where the actual solid structure lies. This wasn't evidence of artificiality. It was barely even an anomaly, more of a curiosity, something that fit less obviously into standard models than most cometary observations, but that didn't clearly contradict them either. NASA scientists who analyzed the images spent significant time investigating this offset. They concluded that it fell within the range of variation seen in irregular outgassing from active comets, that the resolution limitations made precise localization difficult, and that no extraordinary explanation was required. The images were archived. Papers describing the observations would be published in coming months. And that, for most of the astronomical community, closed the question. Yet the offset remained. Documented, measured, unexplained not in the sense of being inexplicable, but in the sense that no single explanation emerged as obviously correct to the exclusion of alternatives. It was one more small strangeness added to an accumulating collection. Chapter 9. The Silence from Radio Telescopes. In August 2025, shortly after 3I Atlas's discovery, several researchers proposed dedicating radio telescope time to listening for potential signals from the object. Not because there was specific evidence suggesting technological origin, but because the opportunity cost of listening was minimal, while the potential value, however improbable, was enormous. The Breakthrough Listen initiative, funded by Yuri Milner, and focused on searching for evidence of extraterrestrial technological civilizations, seemed like a natural fit. They had dedicated time on major facilities, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia. Adding 3I Atlas to their target list would require only modest schedule adjustments. As of December 2025, no results from such observations have been publicly released. This could mean many things. It could mean observations were conducted and detected nothing, with null results considered insufficiently interesting for immediate publication. It could mean observations are planned, but haven't yet been scheduled due to competing demands for telescope time. It could mean proposals were submitted but not accepted because program committees viewed them as low scientific priority. Or it could mean observations were conducted and detected, something requiring careful analysis before public announcement. The challenge with interpreting silence is that silence itself carries no information. We can't distinguish between "we looked and found nothing" and "we didn't look, and we looked and are still analyzing what we found," without explicit statements from the facilities involved. Avi Loeb has noted publicly that he's aware of no systematic radio monitoring of 3I Atlas, which he describes as a missed opportunity, regardless of ultimate conclusions about the object's nature. Radio observations cost relatively little, provide data that can either rule out artificial signals definitively or detect them unambiguously, and create a baseline for future interstellar objects that will inevitably be discovered in coming years. The argument for listening is straightforward. If 3I Atlas were a probe, despite the low probability most scientists assign to this possibility, it might transmit signals for multiple purposes: navigation beacons, data transmission back to its origin point, communication attempts with any technological civilizations in this system, or simply routine telemetry, the electronic equivalent of the constant low-level signals every spacecraft humanity has built emits as part of normal operations. Natural objects don't transmit radio signals in narrowband frequencies. Stars and planets and nebulae all emit radio waves as thermal noise, but it's spread across broad frequency ranges without the focused, structured characteristics that indicate technological origin. A single detection of narrowband emissions from 3I Atlas at any frequency would constitute extraordinary evidence, requiring extraordinary scrutiny, but ultimately providing near certainty about artificial origin. The absence of such detection, conversely, proves very little. An artificial probe not actively transmitting, or transmitting in directions that don't intersect Earth, or using communication methods we lack technology to detect, would be indistinguishable from a natural object through radio observation. So, the silence from radio telescopes, assuming observations were actually conducted, tells us only that if 3I Atlas is artificial, it's not broadcasting signals we can detect with current instruments and methods, which is precisely what we'd expect from either a natural object or a technological one designed for discrete operation. Still, the apparent lack of systematic radio monitoring represents a curious gap in our investigation of the most statistically unusual interstellar object discovered to date. Not evidence of conspiracy or concealment, but evidence of institutional inertia, of scientific conservatism, prioritizing established research programs over speculative long shots. Whether that conservatism will later appear prudent or short-sighted depends on what December's optical observations reveal. Chapter 10. The December Window. From December 10th through December 20th, 3i Atlas will pass through the portion of its trajectory that provides Earth's major observatories their optimal viewing geometry. Close enough for detailed observation, far enough that it's not lost in solar glare, positioned in the night sky, where multiple facilities can track it simultaneously across both northern and southern hemispheres. This 10-day window represents the culmination of 6 months of increasingly detailed study since the object's discovery. Everything we've learned, the mass estimates, trajectory calculations, spectroscopic measurements, visual observations, has been building toward this moment when we'll gather the highest resolution data possible before 3i Atlas becomes too distant to study effectively. The observations planned include optical imaging from Hubble and ground-based telescopes with adaptive optics, capturing surface features at the finest resolution achievable from Earth's distance. These images will show whether the nucleus appears as a single solid body, a contact binary, a fragmented rubble pile, or something less easily categorized. They'll reveal color variations that might indicate compositional heterogeneity. They'll track rotation period and axis orientation with precision impossible from earlier observations at greater distances. Infrared spectroscopy from the James Webb Space Telescope, measuring thermal emission to determine surface temperature distribution. This matters because temperature reveals how efficiently solar radiation is being absorbed versus reflected, which in turn constrains surface composition and structure. A solid rocky object heats differently than a fluffy aggregate of ice and dust. A hollow shell with thin walls would show different thermal response than a solid mass. Ultraviolet observations, tracking the production rates of various gas species in the coma: hydroxyl, carbon monoxide, carbon dioxide, cyanide. Each molecule fluoresces at characteristic UV wavelengths when excited by solar radiation. By measuring emission strengths, astronomers can determine not just what's present, but in what quantities and at what rates it's being released. Changes in these rates, as the object continues its trajectory, will reveal how solar heating affects different regions of the surface. Polarimetry, measuring the polarization state of scattered sunlight. Dust grains of different sizes, shapes, and compositions polarize light differently. These measurements constrain particle properties in the coma, revealing whether the dust resembles typical cometary material or shows anomalies in grain size distribution or structure. Photometry, precise brightness measurements across multiple filters. Comets often vary in brightness as they rotate, with different surface regions having different reflectivity. By tracking these variations over time, astronomers can determine rotation period, how fast the object spins, and possibly map regions of different composition on the surface. All of this data, collected simultaneously by multiple independent facilities, will be analyzed by teams around the world over subsequent months. Initial results typically appear within weeks. Refined analysis takes longer. Peer-reviewed papers describing findings in detail usually publish 6 to 12 months after observations, which means even after December's closest approach, even after telescopes have gathered their best data, we'll still be months away from scientific consensus about what this data reveals. But there are questions these observations can answer definitively, regardless of how long analysis takes. Is the trajectory consistent with purely gravitational motion, or do we see evidence of course corrections? If non-gravitational acceleration is detected at levels inconsistent with the observed outgassing, that would indicate either vastly incorrect assumptions about the object's mass or the presence of forces acting on it beyond simple cometary jet effects. Does the rotation appear stable and natural, or chaotic and possibly controlled? Natural objects tumbling through space for millions of years typically develop stable rotation states determined by their shape and mass distribution. Artificial objects might rotate differently, especially if maintaining specific orientations relative to the sun or other reference points. Are there surface features that can't be explained through natural weathering and impact processes? At the resolution available during closest approach, perhaps a few hundred meters per pixel. For the best instruments, geometric regularity, or structural organization would be visible if present on the scale of the entire nucleus. Does the outgassing pattern show evidence of focused jets that might indicate preferential venting from specific locations? Or does it appear diffuse and symmetric as expected from an irregularly shaped rotating body? This matters because artificial objects might vent gases in controlled ways, while natural comets typically have more random distributions of active regions. None of these observations will prove artificiality. Natural objects can display surprising behavior. Comets are complex, messy, unpredictable, but systematic anomalies across multiple independent measurements, if they appear, would elevate the questions surrounding 3IATLAS from statistical curiosities to genuine scientific puzzles requiring explanation. And that's what December offers. The best opportunity we'll have to either firmly establish this object as a natural, if unusual, interstellar comet, or to document anomalies that future visitors to the solar system might help us understand when we eventually develop technology capable of intercepting and studying such objects directly rather than observing them from millions of miles. Chapter 11. What we still don't know. Despite 6 months of observation by some of the most sophisticated instruments humanity has built, fundamental questions about 3I Atlas remain unanswered. Not because we lack curiosity or capability, but because certain questions can't be resolved through telescopic observation alone. Internal structure. We cannot see inside objects from millions of miles away. All our instruments measure surface properties, reflected light, emitted gas, thermal radiation. Whether the nucleus is solid, fractured, or hollow remains undetermined. Whether it's homogeneous or contains internal voids, chambers, or differentiated layers cannot be established without close-range radar or seismic probing, neither of which current missions can provide. True composition. Spectroscopy reveals what gases are being released from the surface as it heats. It doesn't tell us what's beneath those surface layers. A technological object coated in ice and dust would release the same molecules as a natural comet during solar heating. We detect water, carbon dioxide, organic compounds, everything we're currently observing, without being able to distinguish surface frost from bulk composition. Origin point. We can trace 3I Atlas's trajectory backward through space. But interstellar distances and timescales prevent identifying a specific parent star system. The object could have traveled for millions of years from any of thousands of stars in the galactic neighborhood. It could be truly ancient, older than our solar system, ejected when the Milky Way's chemistry differed from present conditions. Purpose, if any? This is perhaps the most fundamental unknown. If 3I Atlas is technological, a possibility most scientists consider vanishingly unlikely, but cannot completely exclude, we have no framework for understanding its mission. Exploration, resource assessment, survival mission from a dying civilization, automated probe continuing operations long after its creators vanished. The range of possibilities is limited only by imagination, and imagination provides poor guidance when extrapolating from a sample size of 1. These unknowns matter because they define the limits of what December's observations can reveal. We will get better data, higher resolution images, more precise spectroscopy, refined trajectory measurements. We will narrow uncertainty in multiple parameters, but we cannot, from Earth, definitively determine whether 3I Atlas is natural or artificial through remote sensing alone. That question requires either detection of unambiguous signals, radio transmissions, visible propulsion, geometric surface features, at scales our telescopes can resolve, or eventual direct investigation with spacecraft capable of close approach. Neither seems likely in the immediate future. The closest approach on December 15th places 3I Atlas at 1.8 AU from Earth, about 170 million miles. No existing mission has trajectory or propulsion capability to intercept it. Designing, building, and launching a probe to rendezvous with an object moving at 67 kilometers per second relative to the Sun would require years of preparation and enormous cost, justifiable only if initial observations revealed characteristics so anomalous that international cooperation on an emergency basis became politically feasible. Current observations, while unusual in aggregate, do not rise to that threshold. They show a massive object with improbable trajectory alignment, releasing gases consistent with cometary composition. Strange, yes. Inexplicable, no. So, December's window represents our best and likely final opportunity to study 3I Atlas in detail before it continues its journey back into interstellar space, possibly never to be observed again by human eyes or instruments. What we learn in those 10 days will shape how we approach future interstellar visitors. If 3I Atlas proves thoroughly ordinary, despite initial statistical peculiarities, the lesson will be that improbable trajectories sometimes occur through chance alone, that massive interstellar objects may be less rare than current models suggest, and that unusual chemistry can emerge from formation environments we've never directly sampled. If anomalies persist in December's data, if observations reveal features that resist straightforward natural explanation, the lesson will be different. That we need better frameworks for investigating objects whose characteristics don't fit established patterns. That statistical improbabilities deserve systematic follow-up rather than casual dismissal. And that the question, could this be artificial, deserves methodological rigor rather than reflexive rejection. Either outcome advances scientific understanding. Either result provides data for evaluating future discoveries, but only one outcome persistent. Documented anomalies that accumulate into a pattern, suggesting intent rather than chance, would fundamentally alter humanity's understanding of its place in the cosmos. Chapter 12. The pattern we might be missing. Consider a thought experiment. Imagine you're an astronomer in the year 1950, before we had spacecraft, before we understood planets around other stars, before we knew whether technological civilizations might be common or rare in the universe. You're observing the night sky with the best telescopes available, already quite good, capable of detecting faint objects and measuring spectra when you notice something unusual passing through the solar system. It's moving fast, clearly not bound to the Sunday. Its trajectory is oddly aligned with the plane of planetary orbits. It shows faint outgassing that might be cometary, but the chemical composition seems slightly off. The mass appears higher than expected for the observed size, and curiously, it passes near Earth at a suspiciously convenient distance for observation. You note these oddities. Perhaps you publish a paper describing the unusual characteristics, but you have no framework for interpreting them as potentially artificial. The idea that technological objects from other star systems might visit ours hasn't entered serious scientific discourse. SETI won't exist for another decade. The very concept of investigating the question systematically hasn't been developed, so you classify it as an unusual comet, note the peculiar features in the literature, and move on to other observations. The object leaves the solar system. No one ever sees it again. And humanity's first potential encounter with extraterrestrial technology passes unrecognized because we lack the conceptual framework to ask the right questions. This scenario isn't speculation about the past. We have no evidence anything like this actually occurred in 1950. It's a parable about the present. We now possess sophisticated instruments. We have detailed models of how comets and asteroids form and behave. We understand spectroscopy, orbital mechanics, thermal physics. We've sent spacecraft to study comets up close. We know what natural objects should look like across a wide range of conditions, but we still lack a systematic framework for recognizing artificial objects if they're designed not to obviously advertise their nature. We have no established protocols for what observations would definitively distinguish natural from technological origin in objects that don't transmit radio signals or display overtly geometric structures. This is the pattern we might be missing. Not that every unusual object is artificial, but that our methods for recognizing artificiality are optimized for detecting only the most obvious cases: radio signals, clearly geometric shapes, visible propulsion, while potentially overlooking more subtle indicators. 3. Atlas's statistical profile, improbable trajectory, unusual mass to outgassing ratio, convenient timing, chemical peculiarities, doesn't prove artificiality, but it represents exactly the kind of aggregate signature that would appear if an object were designed to mimic natural phenomena while still accomplishing specific mission parameters, like surveying inner planets or using gravitational assists from planetary encounters. A truly advanced civilization building interstellar probes wouldn't necessarily design them to be obviously artificial. Depending on mission objectives, discretion might be advantageous. A probe coated in cometary ice, using natural outgassing for minor course corrections, maintaining external characteristics indistinguishable from debris, would accomplish close approach to inhabited worlds without triggering defensive responses or unwanted attention. This doesn't mean 3IATLAS is such a probe. The natural explanation remains vastly more probable given base rates. The overwhelming majority of objects in space are natural, full stop. But it means we should be thoughtful about what observations would actually distinguish between the scenarios, rather than assuming that current observations definitively resolve the question simply because they're consistent with natural formation. The December observations provide an opportunity to gather data that might help develop those distinguishing criteria. Not to prove 3I Atlas is artificial, that would require far more dramatic anomalies than seem likely, but to establish baselines for evaluating future interstellar visitors when they appear. And they will appear. The Vera Rubin Observatory will find them regularly. We'll detect dozens, then hundreds, then thousands over coming decades. Most will be natural. But if technological probes are even moderately common relative to ejected planetary debris, say, one artificial object for every 1,000 natural ones, we'll encounter them. The question is whether we'll recognize them when we do. Chapter 13. What December might tell us. The observations planned for mid-December will answer some questions, while inevitably raising others. This is how science proceeds, not through sudden revelations that settle all uncertainties, but through incremental refinement of understanding that narrows the range of plausible explanations. What we will definitely learn: precise trajectory. With observations from multiple facilities over the optimal viewing period, orbital parameters can be determined to extreme accuracy. If course corrections occurred at perihelion, they'll become apparent in deviations from purely gravitational motion. If the orbit remains perfectly hyperbolic, with no anomalous accelerations, that constrains scenarios involving propulsive maneuvering. Surface characteristics. Higher resolution imaging will reveal whether the nucleus is a single, coherent body, a loose aggregate, a contact binary, or something less easily categorized. Color variations across the surface might indicate compositional differences. Brightness variations during rotation will constrain shape and potentially reveal non-random features if they exist at detectable scales. Outgassing behavior. Continued spectroscopic monitoring will track how gas production rates evolve as the object moves away from perihelion. Natural comets show predictable patterns determined by solar heating and rotation. Deviations from expected patterns, gas production increasing when it should decrease. Emissions from regions that should be cold and inactive, abrupt changes not correlated with rotation or solar distance would be worth examining carefully. Thermal properties. Infrared observations will measure how the surface responds to solar heating. This constrains bulk properties. Solid objects heat and cool differently than porous aggregates. Icy surfaces behave differently than rocky ones. If the thermal signature doesn't match composition inferred from spectroscopy, that mismatch would require explanation. What we won't learn, regardless of observation quality, internal structure, short of radar penetration or seismic probing, we cannot determine whether 3I Atlas is solid throughout, contains voids, or possesses organized internal architecture. The surface properties we measure don't uniquely specify interior configuration. Ultimate origin. Trajectory tracing backward through interstellar space becomes increasingly uncertain over long timescales. While we can determine the general direction 3I Atlas came from, identifying a specific parent star system among thousands of candidates exceeds current capability. Intent, if any. No passive observation can determine whether an object is following a programmed mission, responding to detected conditions, or simply obeying physical laws applied to inanimate matter. Purpose, if it exists, remains invisible to telescopes. The gap between what we can observe and what we wish we could know defines the frustration surrounding 3I Atlas. We have a genuinely unusual object passing through our neighborhood at the closest distance any confirmed interstellar visitor has achieved. We have sophisticated instruments capable of characterizing it in unprecedented detail. And yet the fundamental question, is this something natural or something made, may remain unanswerable from remote observation alone. This doesn't mean the observations lack value. Understanding what natural interstellar objects look like provides the baseline for recognizing anomalies when they appear. Documenting the chemical composition and structure of material from other star systems teaches us about planetary formation in environments we can never directly sample. Even if 3I Atlas proves thoroughly ordinary, the data contributes to understanding we didn't possess before its arrival. But there's a nagging possibility that bothers some researchers, Loeb prominent among them. The possibility that we're gathering extensive data on an object whose true nature won't become apparent until we either develop technology to investigate it directly, which won't happen in time before it leaves the solar system, or until we've observed enough similar objects to recognize patterns currently invisible in a sample size of 3. December represents the moment when we extract maximum information from this particular visitor before it recedes beyond effective observation. Whether that information resolves current questions or simply refines them into new forms won't be clear until analysis completes months from now. In the meantime, the object continues its trajectory, moving outward, carrying whatever secrets it holds, natural or otherwise, back into the vast dark between stars. Chapter 14. After December, by January 2026, 3I Atlas will have passed its closest approach to Earth and will be receding into the outer solar system, headed generally toward the orbital region of Jupiter. By March, it will pass within 0.36 AU of Jupiter, close enough that NASA's Juno spacecraft, currently orbiting the gas giant, might be able to observe it with onboard instruments if mission controllers choose to dedicate observation time during what would otherwise be focused on Jupiter itself. That March observation would provide the last high-quality data before 3I Atlas becomes too faint and distant to study effectively. After Jupiter, the trajectory carries the object outward beyond the realm of effective ground-based or orbital telescope observation. Within a year or two, it will be too dim to track. Within 5 years, it will be hundreds of AU from the Sun, well into the outer reaches, where only the largest, brightest objects remain visible from Earth. And then it's gone, lost in the immensity of interstellar space, perhaps to encounter another star system in 1,000,000 years, perhaps to drift indefinitely through the cosmic dark, perhaps if it's technological and merely hibernating to activate again when conditions warrant. We won't know. We'll have whatever data we gathered during its 6-month passage through the inner solar system. We'll have papers analyzing those observations, debates about interpretation, refined models of interstellar object populations. We'll have learned things about cometary chemistry, orbital dynamics, and possibly, depending on what anomalies the December data reveals, about the limits of our ability to distinguish natural from artificial when observing from afar. But 3I Atlas itself will be beyond reach. Whatever questions it raised but didn't answer will remain unresolved until future visitors provide additional data points for comparison. And there will be future visitors. The discovery rate for interstellar objects is accelerating rapidly. In the 8 years between Oumuamua's discovery in 2017 and now, we've confirmed 3. The Vera Rubin Observatory's survey capacity suggests we'll find one every few months once the system reaches full operational capability. Within a decade, we might have catalogued hundreds. Most will be small hundreds of meters across, perhaps a few kilometers. Most will pass through the outer solar system, where observation is difficult. Most will be discovered only in hindsight, after they've already made their closest approach and are heading back into interstellar space. But occasionally, one will be large. Occasionally, one will pass near Earth. Occasionally, one will display characteristics unusual enough to warrant the kind of scrutiny 3I Atlas has received. And each one will teach us something about how to approach the question that mainstream science remains reluctant to ask systematically. How would we recognize a technological object if one appeared? This is 3I Atlas's real legacy, regardless of what it ultimately proves to be. It forced the conversation. It made respectable scientists consider scenarios they would normally dismiss. It demonstrated that statistical improbabilities can cluster around single objects in ways that demand more than casual acknowledgement. The question isn't whether 3I Atlas is a probe from an alien civilization. The probability remains low, the evidence remains ambiguous, the natural explanation remains vastly more likely. The question is whether we're prepared institutionally, methodologically, conceptually to recognize the technological object when it eventually arrives. Because if technological civilizations exist anywhere in our galaxy, if they've developed interstellar flight capabilities, if they've sent automated probes to survey neighboring star systems, then statistically, sooner or later, one of the objects we detect passing through our solar system will be artificial. Not soon, perhaps. Maybe not for decades or centuries, but eventually. And when that moment comes, when we're observing something that's genuinely not natural, will we recognize it? Or will we classify it as an unusual comet, note the peculiarities in academic papers, and watch it leave without understanding what we've seen? 3. Atlas might not be that object. Probably isn't. But it's taught us that the question deserves better answers than we currently have. December's observations represent our attempt to develop those answers, to gather data systematic enough, comprehensive enough, precise enough that when we analyze it, we can say with confidence not just what this object looks like, but what it means. Chapter 15. The thing about certainty. There's a particular kind of frustration unique to astronomy. You observe objects millions or billions of miles away. You gather data, images, spectra, brightness measurements. You apply physics, mathematics, statistical analysis. And you build models describing what you're seeing. But you can never truly know. You can never reach out and touch the object, examine it directly, probe its interior, verify your conclusions through hands-on investigation. You can only observe from a distance and infer. This limitation shapes how astronomers think about certainty. In laboratory sciences, you can run experiments repeatedly, vary conditions, test hypotheses directly. In astronomy, you get one observation per event, one supernova, one planetary transit, one close approach of an interstellar object. You can't rerun it. You can't ask the object to pass by again more slowly so you can get better data. You work with what you get. For 3I Atlas, what we get is 6 months of observation as it passes through the inner solar system. 6 months during which it's close enough and bright enough to study. Then it's gone, and we're left with whatever data we managed to collect, whatever questions we managed to answer, whatever mysteries remain unsolved. This creates a particular kind of pressure. Every observation matters because there won't be another chance. Every decision about which instrument to use, which wavelength to observe, which questions to prioritize these decisions, have consequences that can't be undone later. The December observations carry that weight. They're not just another data point in an ongoing study. They're the final opportunity to gather high-quality information before the object recedes beyond effective observation range. And yet, even with perfect execution, even with every major telescope performing flawlessly and gathering data exactly as planned, we'll still be left with uncertainty about fundamental questions. Is it natural or artificial? We'll have better data for evaluating that question. But unless the observations reveal unambiguous artificiality, geometric structures, radio signals, obvious propulsion, the question won't be definitively resolved. It will simply become a more informed version of the same uncertainty we've had since July. What's it made of internally? We'll know surface composition with high precision. We'll have thermal models constraining bulk properties, but internal structure will remain inferred rather than directly measured. Where did it come from? We'll have trajectory traced backward through space, perhaps identifying a general region of the galaxy, possibly narrowing to a few candidate star systems. But we won't know for certain which star, which planetary system, which formation environment produced this particular object. These limitations don't represent failure. They're inherent to observational astronomy. You learn what you can learn from photons that traveled millions of miles to reach your instruments. Everything else is inference, modeling, educated guessing constrained by physical laws but never rising to the level of proof available in experimental sciences. So, when December passes, when the observations are complete and analysis begins, we'll be in a familiar situation. We'll know more than we did. We won't know everything we wish we could. And we'll be making probabilistic judgments about competing explanations rather than reaching definitive conclusions. For most scientists, this is acceptable. Science doesn't require absolute certainty. It requires honest evaluation of evidence and willingness to revise conclusions when new data arrives. Chapter 15. The Thing About Certainty. Continued. If December's observations show 3I Atlas behaving exactly as a large carbon dioxide-rich comet should behave outgassing predictably, rotating naturally, displaying no anomalous accelerations or structural features, then the scientific consensus will solidify around the natural explanation. The statistical improbabilities will be filed away as interesting coincidences, reminders that unlikely events do occasionally occur in a universe vast enough to contain countless possibilities. If the observations reveal persistent anomalies, trajectory deviations, unexplained by outgassing, thermal signatures, inconsistent with composition, structural regularities suggesting non-random organization, then the conversation continues. Papers will debate interpretations. Some researchers will argue for exotic natural explanations. Others will suggest the data warrants consideration of artificial origin. The question won't be settled. It will simply move to a new phase of investigation constrained by whatever data December provides. This is how science works when dealing with unique events that can't be replicated or directly tested. You gather the best data possible. You analyze it rigorously. You argue about interpretation. And eventually, a consensus emerges, not because everyone agrees absolutely, but because one explanation accounts for more observations more elegantly than alternatives. But there's something unsettling about that process when applied to objects like 3I Atlas. The consequence of being wrong, of dismissing a genuinely technological visitor as a natural comet because we lacked sufficient imagination or observational capability, seems vastly more significant than the consequence of being too cautious and investigating a natural object too thoroughly. This asymmetry haunts the debate. Those arguing for natural explanations point out, correctly, that extraordinary claims require extraordinary evidence. They note that we've never confirmed detection of extraterrestrial technology, despite decades of searching. They observe that comets are complex, unpredictable objects, whose behavior often surprises us without requiring alien engineering. They argue that invoking artificiality without definitive proof damages scientific credibility and encourages conspiracy thinking among the public. All valid concerns, all reflecting legitimate scientific values, but those arguing for more careful investigation counter that the cost of a false positive, studying a natural object as if it might be artificial, is merely wasted time and resources, whereas the cost of a false negative, dismissing an artificial object as natural, is a missed opportunity that will never return. 3. Atlas won't pass by again. We won't get a second chance. This isn't an argument that can be resolved through pure logic. It's a value judgment about acceptable risk in the face of uncertainty. How much caution is appropriate when investigating something unprecedented? How much skepticism is productive before it becomes closed-mindedness? Different scientists answer differently based on temperament, training, and assessment of probabilities. Some err toward conservatism, requiring overwhelming evidence before entertaining unconventional hypotheses. Others err toward exploration, considering possibilities that most dismiss as unlikely because the potential significance outweighs low probability. Neither approach is wrong. Both serve important functions in how science advances. Conservatism prevents wild goose chases and maintains standards of rigor. Exploration prevents missing genuinely revolutionary discoveries by looking only where conventional wisdom suggests looking. The tension between these approaches shapes the December observations. Conservative astronomers will gather data focused on confirming natural cometary characteristics, rotation period, outgassing rates, composition profiles. Exploratory astronomers will gather data searching for anomalies, trajectory deviations, structural regularities, emission patterns, inconsistent with natural processes. Ideally, both approaches examine the same data from different perspectives, and if the object is natural, the conservative interpretation will fit observations better. If it's artificial, the exploratory interpretation will identify features the conservative approach would overlook. But this ideal scenario assumes the data will be clear enough to distinguish between interpretations definitively. In practice, astronomical observations are messy. Instruments have limitations. Observations contain noise. Alternative explanations can often account for the same features through different mechanisms, which means December's data, however comprehensive, will likely still leave room for debate. The conversation will continue beyond the observations themselves, into analysis, interpretation, peer review, and eventually into the scientific consensus that takes months or years to solidify. And by then, 3I Atlas will be gone, receding into interstellar space, carrying whatever truths it represents beyond our ability to investigate further. Chapter 16. What it means if we're wrong. Consider two scenarios. Scenario 1. 3I Atlas is natural. It's a massive comet, ejected from a distant planetary system during formation, wandering through interstellar space for millions of years before its trajectory happened to carry it through our solar system. The statistical improbabilities, trajectory alignment, planetary encounters, perihelion timing, are genuine coincidences, unlikely but not impossible, in a galaxy containing billions of star systems, each potentially ejecting material. The mass is high because it formed in an unusually dense region of its parent system's protoplanetary disk. The chemistry is odd because that system had different elemental abundances than ours. The trajectory aligned with our ecliptic plane through pure chance. The timing placed perihelion during solar conjunction by accident of orbital mechanics. Everything we've observed fits within the broad range of natural variation. We were surprised by some characteristics because our models were built on limited samples, mostly objects from our own solar system, and this visitor represents conditions we hadn't previously encountered. But nothing about it actually violates physical laws or requires invoking artificial construction. In this scenario, December's observations confirm natural behavior. Papers are published, documenting the unusual characteristics. Models are refined to accommodate greater diversity in interstellar object populations. The episode becomes a footnote in astronomical history, an interesting object that briefly raised questions but ultimately fit within natural parameters. The researchers who suggested artificial origins are remembered as having pursued a speculative hypothesis that data didn't support. Their careers aren't destroyed. Science allows for wrong ideas, as long as they're proposed seriously and abandoned when evidence contradicts them. But they're reminded by colleagues that extraordinary claims require extraordinary evidence, and the evidence never materialized. Life continues. Humanity's understanding of its place in the cosmos remains unchanged. We're still alone, or at least still without confirmed contact with other technological civilizations. The search continues through SETI's radio telescopes and future interstellar observations. But 3I Atlas isn't part of that story. It was just a rock. Scenario 2. 3I Atlas is artificial. It's a probe built by an extraterrestrial civilization and sent to survey star systems in the galactic neighborhood. Its trajectory was designed to pass near multiple planets for observation or resource assessment. Its mass represents engineered structure, a shell containing instruments, propulsion, perhaps hibernating systems, waiting for specific triggers. The surface coating of ice and dust accumulated during interstellar travel, providing thermal protection and making the object appear natural to casual observation. The outgassing we've measured comes from that surface layer responding to solar heating, exactly as a comet's would. But beneath it lies technology we don't have instruments to detect from millions of miles away. The perihelion timing during solar conjunction wasn't coincidence. It was planned. The object made course corrections behind the sun, while Earth couldn't observe, using propulsion systems so efficient they don't produce obvious exhaust plumes. It's now on a modified trajectory, perhaps captured into a long elliptical orbit, perhaps heading toward a specific destination in the outer solar system, where it will conduct extended observations. In this scenario, December's observations might or might not reveal the truth. If the probe is designed for discretion, if its creators understood that inhabited systems might have technological civilizations capable of detection, they would have ensured it could pass as natural. The observations might show subtle anomalies, trajectory deviations slightly larger than outgassing can explain, thermal signatures that don't quite match composition, structural hints of regularity, but nothing definitive, nothing that would convince skeptics, and so humanity watches the object recede, having documented something genuinely extraordinary without recognizing it. Future historians, when the truth eventually becomes clear, perhaps through detection of other probes, perhaps through direct contact with the civilization that built them, will look back at December 2025 as the moment we had the chance to understand and failed to ask the right questions. The researchers who suggested artificial origins will be vindicated, but decades too late. Their caution was appropriate. Their willingness to consider improbable possibilities was exactly what the situation required. But they were dismissed by a scientific community too wedded to parsimony, too reluctant to entertain ideas that seemed to border on science fiction. The cost of error. These scenarios represent the two ways we could be wrong about 3I Atlas. Either it's natural, and we're wasting energy investigating artificial hypotheses, or it's artificial, and we're missing the most significant discovery in human history because we're too quick to assume naturalness. The costs of these errors are not symmetric. If we investigate thoroughly and conclude the object is natural, we've spent telescope time and research effort. We've published papers that will be read by small audiences of specialists. We've had debates at conferences. We've refined our understanding of interstellar objects. These are normal scientific activities with normal costs. If we investigate casually and miss that the object is artificial, we've failed to recognize evidence of extraterrestrial intelligence when it passed within 170 million miles of our planet. We've watched a probe from another civilization traverse our solar system and dismissed it as a rock. We've demonstrated that humanity, even with sophisticated technology and extensive scientific knowledge, lacks the conceptual framework to identify artificial objects that don't advertise themselves obviously. And we won't get another chance with this particular object. It will leave. We'll never see it again. Whatever information it carried, whatever purpose it served, whatever we might have learned from recognizing it correctly, all lost because we assumed too quickly that the simplest explanation must be correct. This isn't an argument that 3I Atlas is definitely artificial. The probability remains low. The natural explanation remains more parsimonious. Given what we know about base rates, how many objects in space are natural versus how many might be technological. But it's an argument for asymmetric caution, for taking seriously the possibility that deserves serious investigation, even if ultimately disproven, for gathering data comprehensive enough that future scientists, looking back at December 2025, won't be able to accuse us of having observed something extraordinary and not bothering to look carefully. Chapter 17. The Institutional Gap. In October 2025, shortly after 3I Atlas reached perihelion behind the Sun, Avi Loeb published an essay arguing for the establishment of an international organization specifically tasked with investigating interstellar objects for potential technological signatures. The proposal wasn't new. He'd been advocating for something similar since Oumuamua's discovery in 2017. But the arrival of 3I Atlas, with its unusual characteristics and convenient timing, gave the argument renewed urgency. The core premise: we currently have no systematic framework for evaluating whether objects entering our solar system might be artificial. NASA tracks near-Earth objects that could pose collision risks. Various space agencies coordinate on planetary defense. SETI organizations search for radio signals from distant stars, but there's no body responsible for the specific question of whether physical objects passing through our neighborhood might be technological in origin. This creates a gap in our institutional response capabilities. When an unusual object appears, individual researchers can propose observations, write papers, make arguments, but there's no coordinated international effort, no pool of resources specifically allocated to thorough investigation, no protocol for what constitutes sufficient evidence to elevate an object from probably natural to deserving intensive scrutiny. Loeb's proposed organization would serve several functions. Triage. Rate each newly discovered interstellar object on a scale from clearly natural to potentially artificial based on observable characteristics. Objects rating above a certain threshold would automatically trigger coordinated observation campaigns using multiple facilities worldwide. Coordination. Pool data from observatories across national boundaries. Ensure that telescopes in different hemispheres, operating at different wavelengths, using different techniques, all contribute observations to a centralized database accessible to researchers globally. Protocol development. Establish clear criteria for what observations would distinguish natural from artificial. Define falsifiable predictions. Create standardized methodologies so that conclusions drawn by different teams can be compared meaningfully. Rapid response. Maintain readiness to redirect resources quickly when something truly anomalous appears. Interstellar objects move fast. The window for observation is brief. An institutional framework capable of mobilizing major facilities within days rather than weeks could mean the difference between gathering definitive data and missing the opportunity. Communication. Provide authoritative, scientifically grounded information to the public and policymakers. Prevent both premature claims of discovering alien technology and premature dismissals of legitimate anomalies. The response from the broader astronomical community has been mixed. Some researchers support the concept, arguing that systematic investigation of interstellar objects makes sense regardless of how likely artificial visitors might be. The science of understanding natural interstellar debris would benefit from coordinated effort even if no probe is ever discovered. Others object that formalizing this kind of investigation legitimizes speculation better left to fringe groups. They worry that an official organization investigating alien probes would damage astronomy's public credibility, attract conspiracy theorists, and waste resources on questions with near-zero probability of positive answers. Still others point out practical difficulties. Who would fund such an organization? Which countries would participate? What happens when observations suggest something potentially artificial but not definitively so? Does the organization issue alerts, make recommendations, try to communicate with the object? These aren't trivial concerns. International scientific cooperation is valuable but often difficult to coordinate. National interests, funding priorities, and political considerations complicate even straightforward collaborations. Adding the loaded question of potential extraterrestrial contact makes everything more complex. And yet, the gap remains. When 3I Atlas appeared, there was no systematic mechanism for ensuring it received appropriate scrutiny. Individual researchers proposed observations based on personal interest and access to facilities. Some telescopes observed it extensively, others ignored it. Data was scattered across different research groups using incompatible formats. No central coordination ensured comprehensive coverage. This ad hoc approach works adequately when objects are clearly natural, but it risks missing anomalies that would be apparent if data were pooled and analyzed systematically. It creates situations where one group sees something unusual but doesn't realize it's significant because they lack context from other observations conducted independently. For 3I Atlas specifically, we'll never know if more coordinated observation might have revealed features that individual groups missed. The December window will provide concentrated attention, but by then, the object has already made perihelion, already passed Mars. I already completed the portions of its trajectory where course corrections might have been most likely. Ideally, an institutional framework would have been in place before 3I Atlas appeared. The object would have been flagged immediately upon discovery based on its unusual trajectory. Resources would have been allocated automatically. Observations would have been coordinated from July through December, ensuring no critical opportunities were missed. Whether such an organization will ever exist remains uncertain. Scientific institutions change slowly. International cooperation requires diplomatic effort. Funding for speculative research competes with established priorities. But the need is real. We're entering an era where interstellar objects will be detected routinely. Some will be unusual, some will raise questions. And unless we develop systematic methods for investigating those questions, we risk either dismissing genuine anomalies prematurely or chasing spurious signals without proper methodology. 3I Atlas, regardless of what it ultimately proves to be, has demonstrated the need for better frameworks. December's observations will show whether current ad hoc approaches were sufficient. If they weren't, if we missed something important because no one was coordinating efforts systematically, perhaps that failure will provide the impetus for institutional change. Chapter 18. The Dark Forest Hypothesis. There's a particular thought experiment in astrobiology that shapes how some researchers think about interstellar visitors. It's called the Dark Forest Hypothesis, popularized by Chinese science fiction writer Liu Cixin, but originating in earlier work on game theory and existential risk. The premise is simple and chilling. The universe might be full of intelligent civilizations, but they all remain silent and hidden because revealing your presence is dangerous. Here's the logic. You can't know the intentions of alien civilizations. They might be peaceful, but they might not be. They might claim to come in peace while planning conquest. They might have ethical frameworks so different from yours that what they consider reasonable behavior you would consider monstrous. You also can't know their capabilities. A civilization capable of interstellar travel likely possesses technology far beyond your own. If conflict arose, you would be hopelessly outmatched. Given these uncertainties, the safest strategy might be to stay hidden. Don't transmit signals into space that reveal your location. Don't respond to signals you detect from others. Don't make yourself a target. And if you do detect signs of another civilization, the coldly rational choice might be to eliminate them before they can locate you and decide you're a threat. Strike first from a position of advantage rather than risk them striking first later when they've had time to assess your capabilities. This creates a universe where everyone is hiding, everyone is listening, and everyone is ready to destroy anyone they find before being destroyed themselves. A dark forest where predators stalk in silence, where making noise means death, where the only safe strategy is invisibility. The hypothesis provides one possible answer to the Fermi paradox. The question of why, if intelligent life is common in the universe, we don't see obvious evidence of it everywhere. Maybe we don't see it because civilizations that reveal themselves don't survive long enough to become obvious. It's a grim scenario. Most astrobiologists consider it unlikely because it assumes universally paranoid behavior, inconsistent with how cooperation often emerges as an evolutionary strategy. But it's not impossible, and it shapes how some researchers think about what our response should be if we detect something that might be technological. If 3I Atlas were a probe, and again, this remains highly unlikely, what would that mean in the context of the dark forest hypothesis? One possibility: it's a survey mission, gathering information about star systems in this region of the galaxy. Perhaps it's checking for biosignatures, technological signals, anything indicating inhabited worlds. What it does with that information depends on the intentions of whoever built it. Another possibility: it's already gathering information and transmitting it back to its origin point. We wouldn't necessarily detect those transmissions. They might be tightly beamed in directions we're not monitoring. They might use methods we don't recognize as communication. But years or decades from now, the civilization that sent this probe will know about Earth, about our technology level, about our vulnerabilities. A third possibility: darker. The probe itself is the weapon, not a scout sending information back, but an autonomous system making decisions locally. If it detects technological civilizations, if it determines they represent potential future threats, it might already be executing protocols we wouldn't recognize until too late. This isn't paranoia, it's scenario planning. Most researchers consider such scenarios extraordinarily unlikely. Far more likely that 3I Atlas is just a comet. Far more likely that even if artificial probes exist, they're not designed for hostile purposes. Far more likely that civilizations capable of interstellar travel have outgrown destructive impulses. But extraordinarily unlikely isn't the same as impossible. And when dealing with potential existential risks, threats that could affect humanity's long-term survival, even low probability scenarios warrant some level of consideration. So, what would appropriate precautions look like? First, careful observation. If 3I Atlas is technological, understanding its capabilities and behavior patterns provides information about the civilization that built it. Knowledge is the first step in any defensive strategy. Second, discrete monitoring. If the object is transmitting signals, we should be attempting to detect and analyze them. Not necessarily responding that carries its own risks, but listening, understanding what information might be flowing back to wherever this came from. Third, trajectory tracking. If the object makes course corrections, particularly ones that position it for future interactions with Earth or other planets in our system, that behavior deserves attention. A probe establishing permanent orbit around our Sun, positioning itself for extended observation, represents a fundamentally different situation than one simply passing through. Fourth, preparation. Not military preparation necessarily. We likely couldn't defend against genuinely advanced technology anyway, but conceptual preparation, working through scenarios, developing response protocols, ensuring that if something truly anomalous becomes apparent, we have some framework for deciding what to do rather than improvising in crisis. None of this is happening systematically. There's no government agency tasked with monitoring interstellar objects for potential threats. There's no international protocol for responding if an object displays characteristics suggesting artificial origin. There's no plan. This might be fine. If 3I Atlas is natural, if all future interstellar objects prove natural, if humanity never encounters alien technology in our cosmic neighborhood, then the absence of such preparation costs us nothing. But if we're wrong, if something technological does appear, the lack of frameworks for recognition and response could prove costly. Not necessarily in immediate physical terms, we're probably not facing Independence Day scenarios where alien spacecraft attack suddenly. But in terms of missed opportunities, poor decision-making under uncertainty, or failure to recognize risks until they've already materialized. The dark forest hypothesis is speculative. Most scientists consider it an interesting thought experiment rather than likely reality. But it serves as a reminder that our assumptions about extraterrestrial intelligence, that contact would be peaceful, that advanced civilizations are benevolent, that we have nothing to fear from interstellar visitors, are just assumptions. We have no data. We're guessing based on hope rather than evidence. 3. Atlas almost certainly doesn't require invoking the dark forest hypothesis. It's almost certainly not a probe. It's almost certainly not gathering intelligence about Earth. It's almost certainly not a threat, but almost certainly contains an implicit acknowledgement. There's some probability, however small, that our assumptions are wrong, and December's observations represent our best opportunity to reduce that uncertainty before the object moves beyond reach. Chapter 19. What the public doesn't know. Throughout the 6 months since 3I Atlas's discovery, most scientific discussion has occurred in specialized forums, conference presentations, peer-reviewed journals, technical preprint servers. The broader public has remained largely unaware that anything unusual is happening. News outlets occasionally report on the object when major observations are announced. Interstellar comet passes near Mars makes for interesting but not alarming headlines. The stories typically mention that it's the third confirmed interstellar object ever detected, note its size and trajectory, perhaps include a quote from a researcher saying it's providing valuable insights into planetary systems beyond our own. What these articles don't convey, what gets lost in translation from technical papers to public communication, is the genuine strangeness surrounding several aspects of this object. The statistical improbabilities, the mass anomaly, the timing coincidences, the chemical peculiarities. This isn't conspiracy or cover-up. It's the natural result of how science communication works. Journalists interviewing astronomers ask about notable discoveries. Most astronomers, believing 3I Atlas is natural, describe it as an unusual but ultimately ordinary comet. They mention interesting characteristics without dwelling on features they consider explainable through standard processes. The researchers, who think the object deserves more careful investigation as potentially artificial, Loeb most prominently do get media coverage when they make such arguments. But it's typically framed as controversial speculation from outlier scientists rather than as a legitimate scientific question worthy of serious consideration. This framing affects public perception. Most people reading about 3I Atlas come away thinking, there's an interstellar comet passing through. Some scientists think it might be aliens, but most scientists think he's wrong. Nothing to see here, which might be accurate, probably is accurate. But it means the broader population has no awareness that December's observations carry any particular significance, that there's a genuine scientific question being investigated, rather than just speculative claims from attention-seeking researchers. This creates an interesting dynamic. If December's data confirms natural behavior, the public never needs to know there was any uncertainty. The object was a comet. Scientists studied it. Conclusions were reached. Story over. No harm done by not broadcasting every intermediate debate. But if December's data reveals genuine anomalies, features that even skeptical astronomers can't easily explain through natural processes, then suddenly the public learns that something potentially extraordinary was happening all along, and nobody told them. This breeds distrust, conspiracy theories, accusations of cover-up, even when the reality was simply that scientists were waiting for sufficient evidence before making dramatic claims. There's no perfect solution to this communication challenge. Science operates on uncertainty and gradual refinement of understanding. Public communication wants definitive answers. We're not sure yet doesn't make compelling headlines. But 3I Atlas represents a case where the gap between what specialists are debating and what the public knows has become particularly wide. December's observations will either narrow that gap by providing data that settles the question one way or another, or widen it further if anomalies persist without reaching levels that convince skeptics. Either way, the object's closest approach to Earth will occur, while most of humanity remains unaware that there's any question about what it is. The telescopes will observe, the data will accumulate, the analysis will proceed, and months later, after 3I Atlas has already receded into the outer solar system, papers will be published, reaching conclusions most people never knew were in doubt. This is normal for astronomy. Most discoveries proceed this way, but there's something disconcerting about the possibility, however remote, that humanity's closest encounter with a potential extraterrestrial probe might occur without anyone outside specialized research communities paying attention until after the opportunity to investigate has passed. Chapter 20. December 15th. On December 15th, 2025, at approximately 1422 Universal Time, 3I Atlas will reach its point of closest approach to Earth, 1.8 astronomical units, roughly 270 million kilometers, about 170 million miles. In that moment, the object will be moving at approximately 67 kilometers per second relative to the Sunday. It will appear as a faint smudge in telescope images, magnitude 15 or 16, depending on current activity levels, far too dim for naked eye visibility, requiring moderate-sized telescopes even to detect. Its coma will extend perhaps 100,000 kilometers, with a faint tail streaming away from the sun, barely visible against the background star field. From our perspective, it will cross the constellation Virgo, moving steadily toward the region of sky that contains the galactic center. Within weeks, it will fade below the detection threshold of most ground-based telescopes. Within months, only the largest facilities will be able to track it. Within a year or two, it will be effectively invisible, lost in the vastness of space beyond our ability to observe. That moment, December 15th at 1422, represents the culmination of 6 months of anticipation, debate, and preparation. It's the point where 3I Atlas passes nearest to our world, where the geometry provides optimal conditions for observation, where we gather the last high-quality data before the opportunity vanishes. But the moment itself will be unremarkable. There will be no visible event, no dramatic phenomenon, nothing you could point a camera at and capture for posterity. Just an object in space, following its trajectory, as it has been for millions of years before humans existed, and as it will continue to do for millions of years after we're gone. The significance exists only in context, in the questions surrounding this object, in the data being gathered, in what analysis might reveal in subsequent months. The moment passes like any other, distinguished only by our attention and the meaning we project onto it. December 15th will come and go. Most of Earth's population will have no idea anything occurred. Those tracking the object will note the milestone, file their observations, begin analysis. And 3I Atlas will continue its journey outward, carrying whatever truths it represents beyond our reach. In the end, that's what December means. Not dramatic revelation, not definitive answers, but the point where we stop gathering new data and begin working with what we have, where active observation transitions to analysis and interpretation, where the story of 3I Atlas as an unfolding event becomes the story of 3I Atlas as historical record. What we learn from that record, whether it confirms the natural explanation or reveals surprises that challenge our assumptions, won't be clear until months after December passes. The data must be analyzed, cross-checked, debated, peer-reviewed. Conclusions take time to solidify, longer still to reach consensus. But December 15th represents the end of the observation phase. After that date, we're working with what we managed to capture while the object was close enough to study. No second chances. No do-overs. Whatever questions remain unanswered after December's data is fully analyzed will likely remain unanswered indefinitely. That finality shapes how researchers approach the observations. There's pressure to be thorough, to gather every possible measurement, to ensure nothing is missed that might later prove significant. But there's also acceptance that some questions simply can't be answered from remote observation alone. We'll know what we can know. We won't know everything, and we'll have to make peace with that uncertainty, as we do with so many aspects of astronomical observation, where direct investigation remains beyond our technological capabilities. December 15th, 2025, a date that might become historical the moment humanity observed its closest confirmed encounter with an interstellar visitor, or a date that will be forgotten, just another observation of just another comet, that briefly caught attention before fading into the archival catalogs, where thousands of other solar system objects are documented and largely ignored. Which it becomes depends entirely on what the data reveals. This is where the story pauses. Not ends, the object continues its trajectory. The observations will proceed as planned. Analysis will eventually produce conclusions, but the narrative must pause here, at the threshold of December, because what comes next depends on data we don't yet have. 3. Atlas might prove to be exactly what most astronomers expect. A large, unusual, but ultimately natural comet from another star system. The statistical improbabilities will be explained as coincidences that seemed significant only because we were paying attention. The mass will be reconciled with composition through better models. The trajectory alignment will be filed as one of those unlikely but not impossible occurrences that happen occasionally in a large enough sample space. Or it might prove to be something that defies easy categorization. Not obviously artificial, it would take unambiguous evidence like geometric structures or radio transmissions to reach that conclusion. But strange enough, that natural comet doesn't quite capture what we're bade observing. An object that raises more questions than it answers, that leaves researchers debating interpretation without reaching consensus. Or, with vanishingly small probability, it might prove to be something that forces us to reconsider our assumptions about what exists in our cosmic neighborhood, something whose characteristics can't be explained through natural processes alone, something that requires acknowledging the possibility, however uncomfortable, that we're not looking at debris from planetary formation, but at a product of intentional design. We don't know. We can't know until December's observations are complete and analyzed. And even then, we might not know with certainty. Astronomical observation rarely provides absolute proof, only varying degrees of confidence in competing interpretations. What we can say is this: 3I Atlas represents an object unusual enough that careful investigation is warranted, regardless of ultimate conclusions. Its mass, trajectory, timing, and chemistry place it at the boundary of what we consider ordinary, making it worth studying thoroughly to understand whether our models of interstellar objects need refinement. The December observations will provide the best data we're likely to obtain on this particular visitor. What we learn will shape how we approach future interstellar objects as they're discovered in increasing numbers over coming years. And somewhere in that data, in the images and spectra and measurements being gathered even now, lies information that will either reinforce our understanding of how the universe works or challenge it in ways we haven't anticipated. That's what December offers. Not certainty, but data. Not answers necessarily, but information that narrows the range of reasonable hypotheses. Not revelation, but the possibility of being surprised by what we find when we look carefully at something genuinely unfamiliar. The closest an interstellar visitor has come to Earth in recorded history. What it means depends entirely on what it is, and what it is depends on paying attention carefully enough to recognize the truth when the evidence reveals it. December will tell us what we need to know if we're watching closely enough to see it. The rest is just waiting.